Hello, everyone. Hope you all had a good Thanksgiving break. Maybe even if you didn't get to see family and stuff, at least you got a break from classes. So we're in the home stretch here. And we're going to keep working on chapter 13, which is on solutions. Next week, we'll probably have a little bit of time for review as well over all of the information. Your test for these final couple sections won't be this Sunday, it'll be next Sunday, just FYI. So we left off talking about concentrations and different ways of describing concentrations, right? So we had mass, percent, we had mole fraction, and then we had molarity, which is moles per liter. I'm going to give you guys just one problem to work through so we can get a little bit of a refresher on molarity. So let's see. How many liters how do I want to phrase this? Sorry. How many liters of solution contain 55.2 grams of HCl in a 4 molar solution. Okay, so how many liters of solution contain 55.2 grams of HCl in a 4 molar solution? Okay, so with this problem, we're given two pieces of information. We know we have a 4 molar HCl solution. So that's its concentration. We're also given how many grams we have. So 55.2 grams of hydrochloric acid, or the solute. We're trying to find volume. So all of these things relate to this idea of molarity equals moles over liters. If I know my molarity, and in this case, I know my moles, I can figure out the volume in liters. My given information isn't in, My given information isn't in moles, but it's in grams, which is close enough. So we can just do a quick conversion. We have 55.2 grams of HCl. Why say moles over liters instead of moles per liter? Either way, it's saying the same thing. Moles over liters, moles over liter over a fraction bar, or moles per liter, same thing. So if we take it this mass here and we use our molar mass of HCl, we know that 1 mole of HCl is equivalent to 36.46. Come here. Come on, pen. 46 grams of HCl. So that will get us out of grams of HCl, and we'll figure out our moles of HCl. 55.2 divided by the 36.46. And we end up with a mole value of 1.514 moles of HCl. Now, if I want to isolate for liters here, liter will equal mole over molarity, right? Or mole divided by molarity. So I take my mole value, which is 1.514 moles of HCl, and I divide it by my molarity, which we said was a 4 molar solution. And remember, molarity this would be 4 moles of HCl for every 1 liter of solution. So you can even see here when you write it this way instead of with the big M, that the mole units will cancel and you'll be left with units of liters. So take our value, we divide it by 4, and we get a volume of 0.37. Let's make this, instead of 4, let's make this 4.00. Okay, so we have some significant figures. So 4.00 allows us to have 3 sig figs. So we'll go with 0.37. I got 378 liters. You may have gotten 379 depending on your rounding. Questions on molarity and how molarity relates to moles and liters. It's a pretty basic equation. You'll be given 2 and solve for the third. Just note that if you want to use molarity, you've got to be in moles per liter. You can't be in some other unit, like grams or milliliters. Back over to our notes over here. So we left off just right around here with molarity. And the next section is talking about dilution. So what is dilution? Dilution is when we add water to decrease the concentration of a solution. So we add H2O to decrease the concentration. The solution to pollution is dilution. No, that is not true. That would be a horrible way of thinking about it. But when we dilute something, we make it less concentrated. So there's a pretty simple equation for solving diluted solutions. And it's going to be, sometimes you'll see it written as M1 V1 equals M2 V2. Where M1 is your initial concentration and V1 is your initial volume. Your M2 is your final concentration in molarity, and your V2 is your final volume. The ones are talking about your more concentrated thing. Your twos here are talking about your diluted solution. Sometimes you may see, instead of it written like M1 V1 equals M2 V2, you'll see it written as C1 V1 equals C2 V2. In this one, C is standing for concentration, so you can use any units here. In this one, you're sort of restricted to molarity, but again, if you're given something in mass or mass volume, you can use this one, which you'll be fine with that. The only thing you want to do, make sure though, is that your units are the same. So if, let's say your volume, you're going to go with milliliters instead of liters, that's fine. They just have to be like milliliters on both sides. So why is this a useful equation? Well, in a lab setting, we have what's known as a stock room where, if you go back there, you'll find really highly concentrated materials. And it doesn't make sense for a lab to carry every concentration of, let's say, hydrochloric acid. Like I wouldn't want to have 12 molar hydrochloric and 11 molar and 10 molar and so on and so on. What I'd want to do is have like a 12 molar hydrochloric acid, so something really concentrated. And then if I have to run a lab where I need like 3.5 molar, I just dilute it down and make as much as I need for that given class. And so I could actually use this equation to make that happen. So we can look at an example here where it says how many milliliters of a 3 molar H2SO4 solution are needed to make 450 milliliters of a 0.10 molar H2SO4 solution. So how you want to be using solution dilution, we're talking about the same material here, right? This is H2SO4, and this is also H2SO4. The only thing that's happened is we've changed the concentration. All right, after this, we're going to talk about solution stoichiometry. That's when we're going to have actually two different components, two different compounds. Here we have the same material. We're just diluting it. So we want to figure out what our C1, our V1, our C2, and our V2 are. Remember, C1 is referring to your more concentrated thing. So the 3 molar is my more concentrated. So 3.0 molar. It's asking how many milliliters of this concentrated thing do I need? So I need to figure out my initial volume. Like, do I want to use 500 liters of this? Do I want to use just a couple milliliters? We're going to figure that out. My final concentration, my desired concentration, is going to be 0.10 molar. So I'm taking it from a relatively concentrated 3 molar solution down to a 0.1 molar solution. So bringing it down like 30 times. And my final volume here, I want to make sure that I have 450 milliliters of it. Let's say I have 45 students and each student needs 10 milliliters. So that's my desired volume. Now I don't have to convert out of milliliters. I can keep it in milliliters, and I'm just going to plug it into the equation. If I want to solve for V1, I need to get C1 over here. So it's a multiplier on this side, so it does the opposite on this side. So C1 will sit on the bottom there. So V1 is going to equal my C2 V2 over C1. When we plug that in, put your 2's on the top. So we've got our 0.10 molar times the 450 milliliters divided by my 3.0 molar initial concentration. And I like to plug the units in because I know that things will cancel and I'll be left with stuff that I like. All right, so when running this through our calculator, we'll end up with a value of 15 milliliters. So what that's saying is you only need 15 milliliters of this really concentrated material. You can dilute it to 450 and bam, it'll hit that concentration exactly where you want it. So let's run through, I'll have you guys run through one of these. Let's say, what is the final concentration of a 12 molar HBr solution diluted from 135 milliliters to 480 milliliters. Now, in a lab setting, you wouldn't normally do this. You don't just like dilute something and guess what the concentration is or try and figure out the concentration. Usually you're going towards a specific concentration, but just to play around with the equation a little bit. Okay, so in this one, we know our initial concentration, our C1 is equal to 12 molar HBr. It doesn't really matter that it's HBr, but I'll put it in there anyway. Our initial volume is the 135 milliliters. So your initial concentration will always be higher. Your initial volume will always be lower. The opposite is true. Your final concentration, which in this case, we don't know, we've made a random solution here. The final concentration should always be lower and your final volume should be greater. So our final volume here, we said we diluted it to 480 milliliters. So in order to get C2 by itself, C2 will equal V1, C1 over V2. Or our 12 molar HBr times our 135 milliliters divided by the 480 milliliters. Milliliters will cancel and we'll be left with units of molarity, which is great because we're trying to find a concentration. And I got 3.4 molar HBr solution. Yeah, 2 sig figs. So that's pretty easy. Like solution dilution's not bad. The next thing that we're going to talk about, though, is solution stoichiometry. Okay, so it gets a little bit more complicated here. So I don't want you to ever use this if you're doing solution stoichiometry. If there's a balanced equation, you've got to use the balanced equation. So let's review a little bit like what stoichiometry even is, what we know thus far about it. So remember that flow chart where we had grams of A can be converted into moles of A. And we can convert from grams of A into moles of A using molar mass, specifically molar mass of whatever the A compound is. And then we can go from moles of A into moles of B, which is just a different compound. And the way we can do that is by using the coefficients off a balanced equation. So, you know, is it a 1-to-3 ratio? Is it a 2-to-1 ratio? Whatever, we're going to get that off of a balanced equation. And then we were hopping back from moles of B into grams of B. And that was sort of, let's put molar mass of B here. So that should all be review. We already know how to do that. But we're going to add some more limbs to this flow chart that incorporate molarity, mass, and volume. Because what is molarity? Molarity equals moles over liters. So if I know something about molarity and I know something about moles, I can get volume. If I know something about volume and molarity, I can get moles. If I know moles of one thing and I have a balanced equation, I can get to moles of another thing. All sorts of fun stuff I can do there. So let's add another limb up here and say volume of A. So how can I get from volume of A into moles of A? What's the missing component there? It's the molarity. So molarity of A. And when I say A, that's just a generic compound, okay? So I can use the molarity of A to hop from volume A into moles of A. And then I could go from moles of A if I have a balanced equation and go into moles of B. And then why don't we add another limb up here, that's volume of B. How can I go from moles of B into volume of B? This would be, I would need to have the molarity of this compound B. Okay, so let's put molarity of B here. I can actually add another limb here. I'm going to stick it down this way. And in this lower left-hand corner, I'm going to put molarity of A. So maybe instead of being given the volume, I'm going to be given like the molarity, and I want to figure out moles. So let's say molarity of A. How would I get from molarity of A into moles of A? I would use my volume of A. That would be how those connect to each other. And then same thing over here, I'm going to put a limb coming off of my moles of B, and I'm going to put molarity of B. And how could we hop between moles of B and molarity of B? We would use the volume of B to make that happen. So the mole of A to mole of B, that stays the same in whatever path you take. You will always use the coefficients. But we could take a couple different paths here. I could give you the grams of A and want to say find the volume of B, and we could take this path like this here. I could go grams of A into molarity of B, going like this. I could give you volume of A and find volume of B, going like something like this, or we could go like this. There's all these different ways we can travel through, okay? So let's try a problem. And I'll type it up. how many grams of CaOH2 are needed to neutral Okay, so how many grams of CaOH2 are needed to neutralize 25 milliliters of a 0.100 molar HNO3 solution? And I'll give you another thing here. This does come with a balanced equation. So the balanced equation for this is CaOH2 plus 2HNO3 will produce 2 waters and 1 calcium nitrate, NO3, 2. Okay, so a couple indicators that you're going to be wanting to do stoichiometry or use our master stoichiometry flowchart. It's giving us a balanced equation. So that's one good indicator. Another thing is that they're talking about one material here, right? Here they're giving me information about CaOH2. Here they're giving me information about the HNO3. So I'm gonna have to somehow relate this to this, right? So this is where the stoichiometry is gonna happen. So let's look at our master flow chart and figure out kind of what path we wanna take. Compound A is always going to be the material that you have more information on. So I'm actually, why don't I just write that out here? So compound A, in this case, is what I have more information on. So I have more information on this HNO3. So that's going to be my starting compound. And what do I know about HNO3? I know 2 things. I know its volume, which is equal to 25.0 milliliters. And I also know its concentration, or its molarity, which is equal to 0.100 big M. It's HNO3. Okay, compound B is going to be the other thing, right? The CaOH2. What am I trying to find? Well, I'm trying to find grams. So let's go up to our flow chart and see kind of where we're starting and where we're ending. So I am given volume and molarity. So I really could start either here or here. Doesn't matter. I like to start with volume. I just find it easier. So we know volume of A. If we know volume of A, we can use the molarity of A to get into moles of A. If I get into moles of my compound A, I can easily get into my moles of compound B by using my coefficients. And then if I have moles of B, I can get into grams of B, right? Because the final thing it's asking me for is grams. So I'm starting here and I'm gonna end right here. So I'm kind of going down, over, and over. So we want to step our way to this place. So let's start with our volume A. I'll tell you right now, when you're doing solution stoichiometry, if it gives it to you in milliliters, just right off the bat, convert it into liters. because milliliters and molarity are not comparable to each other. So I'm going to say that this is 0.025 liters of solution. Another thing that I like to do is instead of writing my molarity with big M, I'm going to change that into moles per liter because it's just better with stoichiometry. So instead of saying it's 0.100 molar, I'm going to say it's 0.100 moles of the HNO3 in every 1 liter of the solution. This is much more handy for dimensional analysis because we have 2 units. So I'd recommend when you're setting up your work here, if you've got milliliters, get it into liters. If you've got molarity, get it into moles per liter. So first step is to write out our volume of compound A. In this case, we have 0.025 liters specifically of this HNO3 solution. And so the flow chart says, well, if you want to get from volume A into moles of A, you need to use the molarity. So let's use our molarity as our first dimensional analysis step. I have liters on top here, so I want to put the liter on the bottom. So we're good throwing that on the bottom, and then the mole will go on top. 1.100 moles of the HNO3. What happens to my liters? Liters cancel. So we've moved out of a volume value of A and we've moved into a mole value of A. Everybody good with that so far? So the next step is pretty easy. We just use our coefficients. There's a 2 here and there's an inferred 1 here. So 2 HNO3s for every 1 CaOH. So let's go ahead and do that. The HNO3 needs to go on the bottom. So we'll put the 2 HNO3 on the bottom, specifically 2 moles of HNO3 for every 1 mole of the CaOH2. What happens to my moles of, compound A or my HNO3? Those will disappear. And now we have moles of my compound B. So we're getting closer to grams, right? The last step is in order to go from, and if you need the reminder, if in order to go from moles of B to grams of B, we use the molar mass of B. So we need the molar mass of calcium hydroxide, which I don't have off the top of my head, but I've got somewhere 74.1. So 74.10 grams of CaOH2 for every 1 mole of the CaOH2. And the moles will cancel there. So now we're left with just the unit of gram, which was the desired unit. We plug it into our calculator and everything should cancel out, except for that gram. Let's see, we get 0.0926 grams of CaOH2. I'm just going to double check my work. Yep. So any questions on the thought process with that? I mean, we need to do some more practice, but working through this. I think the hardest thing is not even this here, it's this here. It's figuring out what's compound A, what's compound B, what are my givens, what am I trying to get to, and then figuring out the path from there. But if you have access to this flow chart here, it's really all sort of built in for you. You just have to kind of figure out where A is and B is, where your start and your end is. So let's do,
yep. What would be some other ways that you might word a question like that? So in this one you used neutralize, but would you also maybe ask like how much is needed to react with? Or
that we could say how much is needed to react. Neutralize, because a lot of times these solution stoichiometry problems are happening between an acid and a base. So there's a a process called titration, where you have a specific amount of acid bonding with a specific amount of base to neutralize it. So that's why you'll probably see neutralization most often. Okay. Let's try another one that's gonna require you to take a little bit of a different path. So in one, all right, so in one analysis, 45.7 milliliters of a 0.500 molar H2SO4 solution is required to neutralize a 20 milliliter sample of NaOH. What is the concentration of the NaOH? And when I'm saying what is the concentration, I'm asking for the molarity of that thing. So I'm going to have you guys try and work on this one on your own. Obviously, let me give you the balanced equation. 2 NaOHs combine with 1 H2SO4 to produce, doesn't really matter, but 2 H2Os and your salt, your Na2SO4. Right, so start by figuring out what's compound A and what's compound B. What is given for each of them, what you're trying to find, and then look at your flow chart and figure out how to get there. So I'm going to give you all about 7 minutes for that one. That's a nice problem to work on. Obviously, while you're working on it, if you have a question, let me know. Just another 30 seconds or so to finish up what you're working on. Okay, so compound A is going to be my H2SO4. H2SO4. That's what I have more information on. Compound B is whatever I'm asking about. So I'm asking what's the concentration of the NaOH. So I know my volume of compound A. So volume is going to be 45.7 milliliters. And right off the bat, I'm just going to convert that into liters, 0.0457 liters of H2SO4. So anytime there's molarity involved, milliliters isn't going to work. I know my concentration or my molarity is equal to 0.500 big M H2SO4. And again, right off the bat, I'm just going to make that into moles per liter so I can use it as a conversion factor, 0.500 moles of H2SO4 in every 1 liter of the solution. Over here in compound B, we know our volume. Great, so volume is 20.0 milliliters, and I'm just going to convert that as well, 0.020 liters of the NaOH. And then what I want to find is its concentration or its molarity, and molarity equals moles per liter. Okay, I already know my liter value, so this can like get plugged directly into it. So what I need to figure out is moles of NaOH, and then plug it in from there. When looking at our flow chart up top here, we are taking this route. So we have volume of A, and we want to find molarity of B. So we're going down, over, and then down. So let's get started with our volume A. Volume A, 0.045. So our 0.0457 liters of H2SO4. If I take that value and multiply it by my molarity, or the 0.500 moles of H2SO4 in every 1 liter of the solution, right? The liter will cancel. Now I'm in moles of my H2SO4. So now I have to do the stoichiometry. And in this case, we can see that there is a 1-to-2 ratio. So 1 mole of H2SO4 for every 2 moles of the NaOH. So you could stop here if you want with your dimensional analysis and solve for moles, okay? Because if you got your moles of NaOH, then you can just go ahead and plug it into that equation for molarity right here. What I'm going to do is I'm just going to chain on one more thing. I'm going to chain my volume on. If I put my volume down here, 0.020 liters of NaOH, and I don't put anything on top, I just put like a value of 1. The units don't cancel, correct? We don't have that ability to cross, but what do we get? We get mole and we get liter. It's the same thing if you were to plug it in here too, okay? So if you like to just sort of break here and then plug it into the equation, do that. If you like the idea of chaining it all together like this, you can do that as well. When putting it all together, we end up with a final concentration of 2.29 big M of NaOH, or 2.29 moles in every 1 liter of solution. So So if you don't do this initial setup, I feel like this gets really complicated and scary. If you get this laid out really well in the beginning, this sort of kind of happens really easily if you have your flow chart. So I'm going to have y'all do, we're going to do one more. Let's do one more just so that we can have solution stoichiometry done and really know how to do it. This one's going to be sort of similar to the last one. What is the molarity of an NaOH solution? Okay, so what is the molarity of an NaOH solution if 48 milliliters is needed? And we'll give this another sig. Is needed to neutralize 35 milliliters of a 0.114 molar H2SO4 solution. So the balanced equation for this one will in fact be the same as the last one. So I'll just rewrite it here. The 2, come on, 2 NaOH plus 1 H2SO4 gives us the 2 H2Os and so I'll give you all 5 minutes for this one. Hopefully you can work maybe a little faster on this one. Okay. So compound A in this one is, again, H2SO4. Compound B is the NaOH. And by all means, if you have a system that works better for you than this, go for it. This just has always kind of helped me organize my information. So I don't feel so overwhelmed when working with these problems. But if there's another way that you prefer to solve it, that's totally fine. So compound A, H2SO4, we know the volume, which is 35 milliliters. So I'm just going to already convert that 0.035 liters of the H2SO4. We also know the concentration of this thing. So its molarity is equal to 0.114 big M, or 0.114 moles of H2SO4 for every 1 liter of solution. Compound B, I know the volume. In this case, the volume is 0.0480 liters. And we're trying to find the molarity. And remember, molarity is moles over liter. So setup is really identical to the last one. We're just dealing with different numbers. We start with our initial volume for compound A, which is 0.035 liters of the H2SO4. We multiply it by its molarity in just the way that it is. So the 1 liter goes on the bottom, the 0.114 moles of the H2SO4 go on top. Say goodbye to liters. Then we use our coefficients, 1 to 2. Okay, so for every 1 mole of the H2SO4, we end up with 2 moles of the NaOH. And again, if you want, you can stop here and plug it in right there, or chain the volume into it. So I'm just going to stick the volume on the bottom, 0.0480 liters. Just put an inferred 1 up on the top to occupy the space, and we'll end up with moles per liter. And when we plug this into the calculator, we should end up with 0.210 moles of NaOH in every 1 liter, or that's the same thing as saying 0.210 big M of NaOH. Those two things are equivalent. Okay. So do you know that problems can bring in some things with grams? It could give you some stuff on molarity and volume and ask you for values of grams. So just follow your flow chart and follow the steps accordingly. Any questions on those ones that we've worked on thus far?
I thought 0.166 or 0.166 on that problem.
Oh, let's see.
Had it laid out.
Yeah, someone else did too. Let me run it. Let me run it through my calculator again. I have been known to make calculator errors. And I have a huge cut on one hand, and then I have burned fingers on the other hand. So I'm not working with a whole lot here. Okay, times the 0.1 times the 2 divided by 0. All right. Yeah, I did too. All right, I like that. Let's go with that. Let's scratch this. Scratch it. And we'll go with a 0.166. Over here, 0.166. 0.035. Yep, no, that's what I got. Okay. So we'll go with the 0.166. Okay, so back over here. So there is another way that we can express concentration, and it's in something called molality. Now, molality is a little bit different, and it's sort of this like lowercase cursive em. Okay. And molality is going to equal your moles of your solute divided by kilograms of solvent. Now, notice that the top is talking about the solute, the bottom is talking about solely the solvent. Right? A lot of the concentrations we've talked about thus far have been in reference to the total, right? The whole solution, the volume of the solution, the grams of the solution. Here we're comparing solute to solvent. So if we look at a problem here, it says to make a 0.150 little m solution of NaCl, how many grams of NaCl should be dissolved in 500 grams of water to form the solution? So we have the overall M, we know that. We can even plug it in. So we know the 0.150 curly QM is going to be equal to moles of solute. And the solute in this case is NaCl, right? So NaCl divided by, well, we want kilograms of the solvent. In this case, water is acting as our solvent. I have 500 grams of this solvent, but we don't want to plug grams into this equation. You can't do it. So we just need to do a quick conversion or move the decimal over 3 spots, right? If this is grams, then 1, 2, 3 would be kilograms. So 0.500 kilograms. Then in order to figure out, we're not going to get grams. It's saying how many grams of NaCl. We're not going to get grams from this equation. We're going to get moles. So my moles of NaCl will equal 0.075 moles. We just took this value and moved it over here. If I want to go from moles into grams, that should feel like second nature now. 1 mole of the NaCl is roughly 58.4, something like that, 58.4, yeah, grams of NaCl. The moles will cancel and we'll be left with a value of grams. And in this case, we get 4.38 grams of NaCl.
Where does the 0.075 come from?
That is sort of a pause or a mid-step. Sorry, my pen isn't working. Here we go. I'll just use the trackpad. So if I take this 0.150 and multiply it by the 0.500, what do we end up with? Moles of NaCl. Okay, so I was just solving for this thing right here.
Or multiply, not divide. Okay.
Multiply. Yeah, because it's doing a divisor here, so we multiply it over here. So then we can solve for our moles of NaCl, and then from there, just do a quick conversion over to grams.
Thank you.
Okay, so I think we'll stop for today there. I've got another problem referencing molality, but we'll pick that up on Thursday. So if you have any questions, feel free to stay around. If you have any questions on what we talked about here, feel free to stay around. Otherwise, you guys are good to go. Remember, your test is not going to be this Sunday. It'll be next Sunday. So enjoy the rest of your day. And see you all next time.
Thank you.
Bye.